Okay, so we have Clay John from Godot, and they're going to talk about Vulkan in their engine. So please give them a warm round of applause.
Hi, everyone. I'm Clay John. I work for W4 Games, which is a company in the Godot ecosystem that provides some commercial services, cloud products, and console ports, which are things that can't be provided by Godot directly because Godot is a free and open source project, and so we can't do those sorts of things. And I'm here to talk today about Godot and how we use Vulkan in Godot. So first, I want to provide just a bit of an introduction to Godot if you're not familiar with it. Godot is a 2D and 3D game engine. And yes, that's native 2D, meaning that you're editing things in pixel space and you don't have a z-axis or a depth axis anyway, depending on what your paradigm is. It's free and open source, MIT licensed. It's hosted by a foundation and developed by the community. It's a really great project if you're into open source, but also even if you're not into open source. We released Godot 4 just this past year in March of 2023. Godot 4 was a huge step up from what we were doing before. Godot 3 was an OpenGL only engine. Godot 4 introduced support for Vulkan, and other graphics APIs are coming, but it also modernized the internals a lot. So it's something that we're really excited about, and it's resulted in a lot of interesting things. It's a fully cross-platform engine, so we support Windows, we support Mac OS, Linux, Android, iOS, web out of the box. Anything that can be supported in an open source fashion out of the box, we aim to support. And then through third-party companies, we're able to support everything else. So for example, we'll be launching Switch, Xbox Series X and S, and PlayStation 5 ports through W4 Games, but those are also available through other third parties and porting services. So just a bit about the experience of using Godot. Godot uses a scene plus node system for building games. So it's kind of a way of putting building blocks together to make your game in a tree kind of scene. So it's a hierarchical scene. Now, for the performance interested people, that sounds horrifying. It is horrifying to build everything in a scene hierarchy. So in the back end, we use a data-oriented design, what we call servers, in order to organize our data and to avoid having to traverse a scene tree for all of our heavy operations. It supports multiple scripting languages out of the box. GDScript and C# are officially supported. GDScript is our in-house scripting language. It's tightly coupled to the engine. And you can bind whatever you want through C interface. Anything that supports C ABI, you can script in Godot. And we support pretty much everything through the community. And finally, we have different rendering backends. Now we support Vulkan, OpenGL, WebGL, and D3D12, and soon we'll have support for Metal. So that's Godot. It's a growing engine right now. Right now, it's used a lot in indie games. This is just a screenshot from our website showing some games that have come out in the last, I think all of these the last year or two. You might recognize some of them. A few of these are quite popular on Steam. And this is what the editor for the engine looks like. So we build our editor with Godot. So everything you see here is something you can do with Godot. All of the UI and everything, that's all using our 2D renderer. This is just a little tech demo showing volumetric clouds. And you can see there's a lot of different things going on. So we've got a shader editor at the bottom there. We've got a file system. You've got your scene view where you can see the various components that make up the scene. And it's similar for the 2D editing experience as well. So you've got tons of sprites. You've got a dedicated editor for animations. You've got all of the properties for your sprite there. And this is just to show you that Godot does a lot of stuff, right? It's a very flexible, very general purpose game engine. Our users like it that way. We like it that way. And that poses a problem for writing a renderer. Our renderer has to be very flexible, and it has to handle a lot of different content. Now, on top of that, our users love to learn the engine by just trying things out and seeing what sticks. And importantly, they really like to iterate rapidly. So rapid iteration is a strength of Godot, and it's something that our users really like. But it also means that we can never assume that users will do things in the right way or the way that we expect them to do things, because they're just going to try things out, and if it looks good or if it achieves what they want, they're just going to settle with that and then move on to the next thing, because they're making games. They're not making rendering engines. They're not necessarily rendering engineers. If it looks right and their game runs, then they go with it. So we can't make too many assumptions. And so what we aim to do is have good average performance, or good performance in most cases. And importantly, we try to avoid situations where we hit pathological edge cases and performance falls off a cliff. So we want users to be able to just try things out, do what they want to do, and then expect that they'll have acceptable performance. And we really want to avoid the situations where they tweak one seemingly random variable and all of a sudden their game is no longer running. Okay, so that is the background. I want to talk about, I'm going to focus on two main things. I can talk about Godot all day, so I'll spare you. And I'll just talk about two things and give some specific examples of these things. So first, I want to talk about writing an approachable rendering backend. So I've talked a little bit about that already, but I'll go into more detail what that means. And then I want to talk about our Vulkan first approach to writing a rendering backend. So by rendering backend, I mean not the high-level renderer, but our abstraction over Vulkan and D3, D12 and whatnot. We call that our rendering device. Now, when we're designing the rendering device, we have to think about performance versus usability. So like I said before, our users are not rendering engineers, so we can't hand them Vulkan and say, have fun, write your game in Vulkan. They want something else. They want something that's a lot easier to use. So, you know, we have an editor, we have all of this interface. So you can make your game without ever touching any rendering code. But you also have slightly more advanced users that want to do a bit more than that. They still don't want to touch Vulkan. They're still not graphics engineers, but they want to do some things that don't come out of the box. So we try to support that in as usable a way as we can, which means we have to make performance trade-offs. And we do that by exposing higher level concepts through our rendering device. So we've heard a bit about a few RHIs that people have here. We have our own RHI. It's a similar level of abstraction to WebGPU, which you know, everyone who's been here for Vulkanised has some idea of what that looks like. Here's an example, a quite simple one, I think. This is creating a uniform set. A uniform set is essentially a descriptor set. As you can see, it's 5 lines, and it's quite easy to parse what you're doing there. You're creating a uniform, you're assigning its type, giving it a binding index, giving it a resource, and then you can create your uniform set directly from that. So this is the sort of thing that we aim for our users. So they can figure this out without understanding all the complexity behind a descriptor set. And so what we're doing is we are finding the places where we can do work for the user. And if we can do a lot of work to save them from having to do it, or make it so they can only have to do a little bit of work, that's a big win for us. And if we can do it without hurting performance, that's also extremely important. Now, we use the rendering device to write our high-level renderer. So we also care about keeping it ergonomic and making sure that people can understand the abstraction without having to learn everything from scratch. So as an open source project, we get contributions from everywhere. People come out of nowhere and will make huge changes in our renderer, and we love that. We encourage it. and we need to support that sort of thing. So we're going to talk a little bit about what our rendering backend used to look like, and then the changes we made to enhance the situation. So previously, we were hand placing barriers. So our rendering device abstraction just exposed barriers to the end user, which means in our rendering code, we're placing barriers. We had this misguided idea that since we knew exactly what our rendering content looked like, we could hand place barriers in the right places, so we could have as few barriers as possible, but we'd put them exactly where they need to be to solve synchronization issues and keep everything hunky-dory. And we were a little bit wrong about that. We had way too many barriers, and we were also missing barriers in a lot of places where we needed barriers. And we found over time, as the renderer got more complex, it became nearly impossible to hand place barriers. And then we started looking at optimizing for mobile, and we just realized there's no way that we can do this. We were also hand ordering render passes. So we were trying to find the places where we could optimize for overlap between, for example, a heavy compute pass and something doing light vertex work. And again, it worked quite well. You know, the performance benefits were there, but as the complexity of the renderer increased, it became harder and harder to manage that. So it worked okay, but we weren't super happy. We were getting synchronization errors that were tough to track down. And ultimately, we want our users to be able to modify the rendering process a bit more, or insert their own code between our rendering passes. And then that becomes a nightmare, because I can hand optimize by putting a barrier where it needs to go. But if I can't make any assumptions about what the user is doing, I'm either going to be throwing in way too many barriers, or we're going to be missing barriers. And then we're going to be exposing barriers to our end users. And it's tough enough for us to manage. It's going to be nearly impossible for them. So we had to come up with a solution for this. We've now, those of you who are attending here, have seen a few solutions. Our solution was a directed acyclic render graph. The approach we took was inspired by an article by Pavlo Muratov. I've linked it at the end of the slide if you want to take a look. It's quite good. But ultimately, we were scared off from the idea of a render graph for a very long time. We didn't like the idea of asking our users to provide all the information that you would typically have with a render graph, outlining all of the resource dependencies that they had, and essentially having these big verbose chunks to set up the nodes of your graph. So we avoided it for a very long time. But in the end, we found something that we could make a little bit automagic. So because we control the rendering device API, we have access under the hood to a lot of information that's useful for creating the graph. And we ended up finding that we had enough information that we can create the graph under the hood, reorder the graph to optimize render passes, and insert barriers as needed without the users having to change their code at all, because users are already using the rendering device API, and so it just works. The only thing that changed on our high-level API is we completely removed barriers. So when you look at the changes we made to our high-level rendering code, for example, all we did was remove barriers out of our high-level rendering code, and then it continues to work, except now our synchronization issues are mostly gone. We still have a few tricky ones left that we're working on, and we have far, far fewer barriers. So how does this approach work from a very high level? Because we've already heard render graphs described a couple times now. So we record commands, and this is through the rendering device API. A command is either an update copy or clear to a text or a buffer, or it's submitting a render list or compute list. So render list is like it's a render pass, essentially. You're bundling in a bunch of draw commands, and you're specifying write attachments, color attachments, depth attachments, whatnot in that. And importantly, we make the assumption that commands always start and end from a valid state. We can ensure that because, again, we control the rendering device API, so we ensure that commands are always starting and ending from a valid state. and we infer the commands from the rendering code. And what this allows us to do is create a node in the graph for each of these commands. And there ends up being very, very few commands, even in a complex scene, because most of the work you're doing is within a render pass, which is just a single node. And so importantly here is our users have no idea that there's a graph going on behind the scenes. They just submit the code the same way they did before, and we record those commands, build the graph, and do everything behind the scenes. Now there is one catch there, and this was discussed a bit earlier today. Commands have to track all the consumed resources and how they're used. So when you have a medium to large scene, we were testing on a scene with about 25,000 resources, which are mostly textures and vertex and index buffers. It's a lot. And that comes with a lot of overhead to track all those resources and ensure that you're doing the right thing with them. By doing that, though, we're able to automatically minimize barriers, and we were able to automate all the resource transitions, which made things really nice. What we realized when we were implementing this is that most of those resources, most of the time, you create a texture when the engine loads, and you never touch it again except to sample from it. So we introduced the concept of immutable resources and mutable resources. And we did it in a way that is a bit automagic. So for certain things, for example, if you're creating a vertex buffer that's being used by a particle system, we know it's mutable. So we're able to infer automatically that's a mutable resource, so you're going to have to track it. If you create, for example, a mesh and you load it through from a GLTF file or something, we assume it's immutable until you operate on it. And then we say, oh, surprise, okay, that's mutable. And for the rest of the run of the program, it'll be treated like a mutable resource. So what that means is the first time you mutate a resource, you end up having to add a bit more state tracking to make sure that things are working for that frame. But every frame after that, it just works. So we traded off essentially a little bit of extra work up front to ensure that we could massively reduce the amount of work that comes later. So we found that this reduced the cost of tracking significantly. And in fact, in all the scenes we tested, we were tracking less than 10% of resources. And those resources are frame buffers, they're compute buffers used for compute effects and particle systems and things like that. So you can't avoid tracking those things, and it tracks them quite well. So the result of this was a decrease in frame time. Primarily, we all care about performance. So we saw about a 10% decrease in frame time, and that's across the board. We saw that on mobile, we saw it on laptops, we saw it on dedicated GPUs. I attribute most of that gains to the huge decrease in barriers. We saw a reduction, depending on the scene, of 60 to 80% reduction in barrier usage. So it goes to show how badly we were misusing barriers, because of course this is also introducing barriers that weren't there before, and just massively reducing the number of barriers that we had, as well as solving a lot of synchronization issues. So we had quite a few. They're mostly gone. We have some particular synchronization issues we're working on, but this has overall resulted in both performance and stability improvements. And importantly, users no longer have to write barriers, and we don't have to worry about resource transitions. Now, the flip side is we are recording and resubmitting commands. So there's some CPU overhead to this technique. But at the same time, we found that we were saving a lot of CPU time on API calls that were unnecessary. So the net cost was quite low. It's tough to measure because it's different for every scene. Some testing indicates that actually we gained more CPU time than we lost. Other scenes, there's a small measurable impact. But overall, the trade-off was something that we were quite happy with. Okay, I'm going to skip through a little bit for the sake of time. So I want to talk about basing this rendering device on Vulkan. So we are big believers in platform-independent APIs. We were really hoping for a write once, run everywhere solution. Obviously, that's not possible, and it doesn't seem like that's going to be possible, but Vulkan got us quite close. Our abstraction is shared between our mobile and our desktop-focused renderers, and a lot of our code is able to be shared, and we're quite happy about that. So I say we designed our abstraction around Vulkan, but that's actually not quite true. We designed it around multiple APIs, but we cherry-picked the things we really liked from Vulkan, and we made sure to make those core parts of our interface. So when we first wrote it, we had Vulkan-style barriers, pipelines, specialization constants, render passes, and a few other things. Obviously, we've gotten rid of barriers now from our API, but that was still something that we started with. And so I'm not going to have time to talk about all these things. I just want to talk about specialization constants and how much we like them and how useful they've been for us. So we love them. We use them to manage shader permutations. Writing a general purpose engine, it's extremely hard to manage shader permutations, because even if you have tight limits on what you do, your users can do whatever they want, right? And our users write, custom ways of parsing together shaders by mashing text together, and they can do whatever they want, and they do whatever they want. And so we want to protect them from the shader permutation problem a little bit. And so one way we do that is making use of specialization constants. We use them a lot for performance settings and things like that, where we can just change a value and then change the structure of the internal shader. So what that looks like, this is just an example from our main 3D render forward clustered pass. So you can see the sorts of things that we're using it for there are either to turn on or off advanced features or to set some performance constraints, so sample counts and things like that. And that allows us to achieve better performance numbers while still keeping permutation count down. Now, specialization constants are great, but they have poor support on certain devices. We found, especially for lower end mobile devices that are not getting driver updates, there were problems. Luckily, the worst problems we found were on devices that partially implemented them. There was no catastrophic issues, but what we found is quite a few devices will use will allow for dead code elimination with specialization constants, but in other places, they weren't performing the same optimization. So for example, in loops, they weren't properly flattening loops when we changed our specialization constants. And of course, they're not supported in D3D12, which was an important target for us in the short term. So what do? We emulate them. Emulating specialization constants on low-end devices that are still Vulkan-based, it's very easy. We just patched the SPIR-V during pipeline creation. We love SPIR-V. This was super simple for us to implement, and it works really well. We wrote a very simple SPIR-V parser, and then we just replaced the specialization constant with a constant, and it works really well. It's a small cost. We measured about 100 microseconds. That's running on a very low-end mobile card. So we felt that the performance trade-off was worth it because we were seeing a huge improvement in runtime performance. And the solution for us is just to only enable that on problematic drivers. Now, I see that I'm running out of time, so I'm going to go very quickly through the next part. Emulating specialization constants on D3D12. We had 2 attempts at this. And so the first attempt I'll describe very, very quickly and then focus on the second attempt. So D3D12 does not have specialization constants. You use constants or you use preprocessor definitions, and then you compile your entire shader again. And that was totally unacceptable for us. The performance overhead would be way, way too high. SPIR-V Cross has some helpers for this, but you're still recompiling. So what do? We patch the DXIL directly. I've got a lot of details about how we did that. I'm going to skip right past them. because we ended up switching away from SPIR-V cross and using Mises near instead for totally unrelated reasons. Near also doesn't support specialization constants in the way we want. We want to have a patchable DXIL blob so that we can patch it the way that we can patch SPIR-V. So what we ended up doing is during the SPIR-V to near pass, we transformed the specialization constant ops into a special one that we've defined, our near intrinsic load constant non-op. And non-op means do not optimize this special operation that we've created. And we pass a placeholder value, which is a kind of a token that says what it is and the identifier. And then we let near optimize as usual and output DXIL. And then at the end of that process, when we're emitting one of these special operations, we just swap it out for a regular load with the constant ID and a default value. And then in the per pipeline, we are able to patch the DXIL directly because we can easily find those operations and put in the value that we want. And then we have to, of course, still re-sign the DXIL container. We found that this was slightly faster than our first attempt. It's of course slower than what we get through Vulkan, but it's quite fast, and the trade-off ended up being totally worth it for us. This second approach is slightly better than the first, but I didn't talk about the first. And so we found that this was good enough. And finally, because I can't help myself, I want to show off a demo scene that we're working on through W4. This is running in Godot, and just want to show off how good it can look. And please let me know if you have any questions. Thanks.
Hey, thank you for the talk. So from the way you described, it sounds like you have to rebuild the render graph structure every frame. So I was wondering if that assumption is true, first of all. And second, how do you make it fast? Because in some other implementations of render graphs, that was quite the pain point to rebuild it.
Yeah, that's a good question. We do rebuild the graph every frame. We've looked at ways of doing partial rebuilds, and everything that we attempted ended up being much, much slower because realistically, the way we've structured the commands or the nodes, they're quite large. So a render pass contains a lot of work, and users aren't doing that many texture updates in the middle of rendering. They typically do a few at the beginning of the frame, and then things go on like that. So our graphs are actually very small. We're not talking about thousands of nodes. We're talking about dozens at most. And for simple scenes, we're talking about dozen. And so the cost of rebuilding the graph is actually extremely, extremely light.
Thank you for the presentation. I was very interested by your shader compilation pipeline. And I was wondering, what is the shading language you are using, and what's your plan for shader cross compilation with on Metal, for example? And that's the first question. And the second question, if I may, it's continuing on my obsession with profiles, and how do you handle your application to work on the user device, concretely in terms of feature or driver bug, all that stuff?
Good questions. We use GLSL everywhere. Internally, we use GLSL. Users use essentially a modified GLSL with some helper functions. And then, so that's what we use internally. For Metal, I believe, I'm not the one working on the Metal backend, but I believe we're using SPIR-V cross, and then doing some trickeries like we're doing with D3D12. In terms of managing features and profiles, we mostly target Vulkan 1.1 with a couple extensions. And then we manually enumerate the things that we absolutely need on project load. And then we manually check for support for features that we can't do without. So things like cube map arrays, we'll do an early out and fail if they're not supported. But our approach is very bare bones right now. And as as we expand to more and more platforms, I think it'll grow with necessity. If that answers your question.
Question over here.
So you said that you want to avoid performance cliffs if a user goes and plays around with something. I was wondering if with the immutability tracking, have you seen any performance cliffs where they start touching a resource and modifying it and it causing performance hits?
We haven't seen that. I would be very interested if we do see it. Basically there, in order to run into a performance cliff, the user would have to issue like a texture update or buffer update or something thousands of times in one frame. But the performance cliff you get in that case is just that you have to rewind to the beginning of your graph and replay the graph again with proper tracking. So what you end up doing is duplicating the cost of building the graph that frame. So if the user had 20,000 textures and then one frame, they're like, you know what? I'm updating all 20,000 of my textures. We would end up rebuilding the graph 20,000 times. So in that case, the performance cliff is there. But I feel comfortable saying that that is such a uncommon case that we'll deal with it if somebody comes to us and says that they decided to update every single texture in their entire game in one frame. But fair point, there is a performance cliff there, a sneaky one.
You said you have a DX12 and Vulkan backend, and I suppose your bar optimizations work applied for both. I just want to know if you notice similar gains on overall performance and the CPU overhead savings between DX12 and Vulkan.
You know, personally, I haven't seen the numbers between DX12 and Vulkan. The layer for building the render graph is above both backends, so I would expect similar numbers in terms of performance, not as much on DX12 though, because barriers are much less of a problem there. And so I would expect some small benefit. The overhead will be the exact same, but the benefit I expect would be less, but I don't have numbers for that, sorry.
So this NIR thing looks enticing. Could you maybe tell me how much effort it is to kind of build it and include it into your code base, you know, as a library? And do you have to like take the whole of Mesa with it?
So that's a good question. We ship a trimmed down .lib or whatever the equivalent is for your platform. We trimmed out everything that we didn't need from Mesa, and we host a repository where you can use it if you want.
That's really nice.
And originally we actually just included all the source from near in the Godot source. It was maybe 100,000 or 150,000 lines of code. We ended up moving it to a shared lib because we wanted to keep our Git repo small. And also Godot is a very small engine. The entire engine with editor is about 150 megabytes. When you ship the engine with your game, it's about 30 megabytes. So adding 150,000 lines of code was actually a bit problematic because you know, it ends up being like a 5% increase in the size of the application, which we didn't like. So we host in a separate repo. It's very easy. Users just download the libs and link it when they're building the engine. Most users don't build the engine themselves, so they don't even have to think about it.
So does that mean that you will have to implement the PlayStation backend for NIR? For code gen?
So I'm not the person working on PlayStation 5, so I can't answer that question directly. The solution for PlayStation is most likely going to be different than D3D12.
All right, we have one last question.
I do see a common challenge in the open source community, like Hydra has it, Blender has it, Godot has it, and that is the abstraction layer of your render device. Do you think that you would be open into abstracting that away into an open source library where we could at least everyone look into or learn from?
It's a very enticing idea for me. Personally, I think if the web GPU spec had finalized 3 years ago, I think we'd be using web GPU. That's a personal opinion. So the idea of abstracting something like that out into something that could be used by everybody is very interesting to me. At the same time, we made a lot of decisions in ours that are focused on our expected user base. We've trimmed a lot of API things that we confidently say our users won't need, but I can't say the same about users for other people. So I don't know if, I mean, we certainly wouldn't want to be the ones maintaining that for that reason, because we like to keep things simple and totally focused on what we do. But personally, I think there's room for something like that, and I'd really love to see it. But I think that's web GPU. But we'll see.
Okay, and one more round of applause for Clay.